In this video, we are going to discuss the residue theorem, which provides a powerful tool for calculating both complex contour integrals and real definite integrals. This is our overview slide, which we'll spend about 5 minutes going over before we talk about these two main topics in more detail and with more examples. We are going to start by talking about the residue of a single pole. So we'll consider an integral of a function w on z on an arbitrary closed contour in the z-plane. So here is our integral over c of our function w of z. Assume that wz has one singularity inside c and that wz can be expanded in a Laurent series about a point z0, such that contour c is entirely within the convergence region. So this is our picture here. We have our contour C, and then we have our, we're expanding a point around the point Z0, but somewhere in here is a singularity, so we're only looking at this annular region here for convergence, and C is inside that region of convergence. And note, because there's WZ is not analytic everywhere inside of C, so it's not analytic right here in the dotted portion, we need to do a Laurent series and we can't do a Taylor series. Consequently, the series can be substituted for WZ in the integral. So in our integral over here, over C of WZ, we're going to substitute the Laurent series expansion for n equals negative infinity to infinity, our coefficient times z minus z0 to the nth power. Then what we will find, and we will develop this later in our video, the c to the negative 1 coefficient, in other words, the coefficient when n is negative 1, is referred to as the residue at the singularity. And we will find that the integral of over c of w of z is equal to 2 pi I times our residue, that is the c to the minus 1 coefficient. And in our video, we will develop this formula further. The second topic we will have is expanding to residues for integrals surrounding multiple poles. And what we will find is the integral around c of wz is equal to 2 pi I times the sum of the residues of all the poles inside c. So the extension for several poles is straightforward. If we have a function wz, which is equal to f of z, which is analytic everywhere, divided by z minus a, z minus b, and z minus c. So we have the picture with a, b, and c. These are all poles. We want to consider an integral of wz on a closed contour c that encloses two of the poles. We'll say we'll enclose point A and point B. The third pole, z equals c, is going to be outside the contour of c. Then what we'll see is the integral over c of wz is equal to 2 pi I times the sum of the residues of poles inside c. So in other words, 2 pi I times the residue of a and the residue of b. Remember, the residue being the c to the minus 1 coefficient of the Laurent series expansion. Our last topic is, as you can see, to calculate the residue over here for all of these problems, we need a Laurent series expansion. But there are cases, and not all functions, but there are some cases where we can use this simplifying function here to find the residue. So we'll look at this formula here for finding the residue of a simple pole, and this general residue formula for poles of order n. And again, these don't always work with every function, so I'll show you a function that we can't use this, and I'll show you an example where we can. That is our overview. We'll go back and start with a residue of a single pole. To develop this formula for a residue of a single pole, we're going to start by considering an integral of our function w of z on an arbitrary closed contour in the z-plane. So our integral I is going to be the integral over c of w of z. Assume that wz has one singularity inside c and that WZ can be expanded in a Laurent series about a point Z naught, such that the contour C is entirely within the convergence region. So here is our illustration. We have our contour C, and inside we're going to expand our function WZ around this point Z naught. But in here, inside, we do have a singularity inside this dotted line. So remember, the point of Laurent is we started with this path that didn't close, like the circle didn't close, but then we deformed it until eventually it became this annular region, which is analytic and converges, and so we could then integrate over our function C. So this is our picture, and consequently, the series, the Laurent series, can be substituted for WZ. So in our integral I over here, integral I over C of WZ, we now substitute for WZ this Laurent series. We are going to break up our Laurent series into 3 different portions based on our integer exponent n. So n can be greater than or equal to 0, or it could be equal to -1, or it could be -2, or some integer less than -2. So this covers all of our exponents, integer exponents n. We will start with n greater than or equal to 0, and for that we are going to use the Cauchy integral theorem. So let's review that really quickly. The Cauchy integral theorem was the really nice theorem because it said if you're integrating WZ and WZ is analytic in some region of the complex plane, if we have an integral along a closed contour C which lies entirely within the analytic region, then the integral is equal to 0. So here is our contour C, and on C and inside C, W is analytic, then the integral around C of WZ is equal to 0. So our example was z squared over z minus 2, and our C, our curve, is the circle of radius 1. So here's C, and our function, you can see, is not analytic at z equals 2, but z equals 2 is outside of our curve. On our curve and inside of our curve, this function is analytic everywhere, and therefore the integral is equal to 0. Coming back to our case for n is greater than or equal to 0, well here the function is analytic everywhere. The z minus z naught is in a numerator, not a denominator. In fact, there's nothing in the denominator unless it's in the coefficient. So it's analytic, and because it's analytic everywhere, the function is analytic, and by Cauchy, that means the integral around a closed curve C will equal to 0. And to summarize, we have the statement for n greater than or equal to 0, its contribution to I must be 0. Now we are to our next case, and we will start with n is equal to -2. We will be using Cauchy's integral formula, so let's do a quick review of the integral formula. The Cauchy integral formula says let f be analytic everywhere inside and on a simple closed contour C, taken in the positive sense. Then the integral over C of f, this is what's analytic, over z minus z naught. So you can see f over z minus z naught is not analytic everywhere. There's a 0 at z naught, a singularity at z naught. But f of z is analytic everywhere. So if f is analytic everywhere, and we have this function here, f over z minus z naught, integrated over c, then the answer is going to be 2 pi I f of z naught if z naught is inside of c, and 0 if z naught is outside of c. Our example is the integral over c of z over z minus 1, where c is the circle of radius 2. This is our picture. Here is our c of radius 2. And then our z naught, that is where our singularity is. But you can see that z is analytic everywhere. So by Cauchy's integral formula, our integral of f of z over z minus z naught is equal to this 2 pi I f of z naught if z naught is inside of c. And that's the case we are in. Our singularity is inside of c. So that means our integral is equal to 2 pi I f of 1. So 2 pi I f of 1, plugging 1 into our f of z is equal to 1. So our final answer is 2 pi I. We also have this general form of Cauchy's integral formula for when we have powers greater than 1 over here in the denominator, a z minus z naught raised to a power greater than 1. And our example is the integral over c of e to the 2z over z to the 4th, where we have a circle of radius 1. Comparing this e to the 2z over z to the 4th to this integral over here, you can see f of z is equal to what's on top, the e to the 2z. What's on bottom, z minus z naught, that'll be z minus 0 raised to the n plus 1. Since this is 4, that must mean n is equal to 3. So then, now putting this on the left-hand side, that means our integral is equal to 2 pi I over n factorial, just moving this to the other side. The nth derivative, in this case n is equal to 3, the third derivative of f evaluated z naught. So 2 pi I over 3 factorial, this is n factorial, the nth derivative of f. So here I took the first, second, and third derivative of f, and I evaluated it at z naught, and z naught in this case is 0, so I get 8. So I have 2 pi I over 3 factorial, 8 times e, 2 to the z naught is 0, so I simply get 8 pi I over 3. Now if we consider n equals negative 2, we have our coefficient c minus 2 times our z minus z naught to the minus 2. You can also write it c to the minus 2 times 1 over z minus z naught squared. Now we can copy our Cauchy integral formula over here, and remember this is good for when our exponent in the denominator is equal to 1. Our generalized formula is when our exponent is greater than 1. Our exponent is 2, so in this case n is equal to 1. And that leads us to this integral of c to the negative 2, that's our coefficient, over z minus z naught squared, that's this portion here, is equal to, moving this fraction over to the other side, remember n is equal to 1, so it's 1 factorial, which is just 1, and this is 2 pi I. So moving it over to the other side, we just get 2 pi I, and where n is equal to 1, the first derivative of c, our coefficient, our c to the minus 2 coefficient, evaluated at z equals z naught. The derivative of our c2 coefficient, which is just a constant, is equal to 0, and therefore the contribution for all terms n equals negative 2 is 0. You can make the same argument for any exponent less than negative 2. Its argument is contribution to the integral is going to be 0. Then our last case for f equals negative 1, the c to the minus 1 coefficient is referred to as the residue at the singularity. And in general now, we're going to have our integral over wz is equal to 2 pi I f of z naught. And our f of z naught f is what's above the z minus z naught. In this case, that's just our residue to the c minus 1. So this is the only thing that contributes to our integral. And this is our final answer for the residue of our single pole. The integral over c of wz is equal to 2 pi I times the c minus 1 coefficient of the Laurent series expansion. We are going to go straight into considering the residue for integrals with multiple poles because it is a natural extension. So if we have wz equals f of z over z minus a, z minus b, and z minus c, where the numerator, f of z, is analytic everywhere, we have poles at a, b, and c. Let's consider the case where a and b are interior to c, our curve c, and the point c, the singularity point c, is outside the curve c. We want to know the integral over c of w of z. So by deformation, we can take this curve c and make it into two curves, one around a and another curve around b. So our original integral I over this original curve c of wz is equal to integral c1 of wz plus c2 of wz, where c1 goes around our first singularity, c2 goes around our second singularity, which means now that our integral I is equal to 2 pi I times the residue of a plus 2 pi I times the residue of b. In other words, 2 pi I times the summation of the residues of the poles inside C. I have this formula written here so that we can start doing examples. So let's consider the integral around C, where C is the positively oriented unit circle z equals 1, since it's a unit circle. And we want to integrate z squared sine over 1 over z. First, let's note that z squared sine of 1 over z is analytic everywhere except at z equals 0, and which is inside of our curve, our circle, our unit circle of radius 1. By our residue theorem, that means the integral around c of z squared sine over 1 over z is equal to 2 pi I times the residue of the poles inside this one pole here. The first thing we need to do then is consider the Laurent series expansion of z squared sine of 1 over z. And we're going to start by looking at the Laurent series expansion of sine of z. Sine of z is analytic everywhere, so the Laurent series will become a Taylor series. And this is a problem we had done when we were looking at Taylor series of real functions sine of x. This is the work here. I kept it here for your reference, but we'll skip down to where we say f of x is equal to x minus 1 over 3 factorial x cubed, and the next term would be plus 1 over 5 factorial x to the 5th, and then minus 1 over 7 factorial x to the 7th. I have written my Taylor series expansion, also my Laurent series expansion of sine of z here. But remember, we actually have sine of 1 over z. So what we can do is plug in 1 over z for z, sort of like we used to do with the basic Taylor series. Now we can just do this also with this series here. So I get 1 over z, 1 over 3 factorial, 1 over z cubed, 1 over 5 factorial, 1 over z to the 5th, minus 1 over 7 factorial, 1 over z to the 7th. And next I'm going to multiply the sine of 1 over z by z squared. So I have z squared times my series, which gives me z squared times 1 over z gives me z. Z squared divided by z cubed gives me 1 over z. This is going to be the term, this is my n to the minus 1 term, which means my residue is minus 1 over 3 factorial. So I can stop once I get to this term because I'm looking for my residue. And I found my residue is equal to minus 1 over 3 factorial, which means my integral of z squared sine of 1 over z is 2 pi I 1 over 3 factorial, which is equal to minus pi I over 3. As you can see, for this residue theorem, having the Laurent series expansion and being able to get the c to the minus 1 coefficient is important to be able to use this formula. There are certain functions where you can use the simplifying formula for getting the c to the minus 1 coefficient, and so it saves you the trouble of having to calculate the Laurent series expansion. So we'll look at the simplifying residue formula for simple poles and the simplifying residue formula for poles of order n. I have our simplifying residue formula for simple poles here for your reference, and our first example is to find the residue at z equals a of wz equals sine of z over z minus a, z minus b. So we have first order poles at z equals a and z equals b. To find the residue at z equals a using the simplifying formula, we're going to take the limit as z approaches a of wz z minus a. So the limit as z approaches a of our sine of z, z minus a, z minus b times z minus a that will simplify, get rid of our pole, z minus a, and we have the limit as z approaches a of sine of z over z minus b. Plugging in a in for z, we get sine of z, a minus b. So this right here will be our residue. We are going to contrast that with our previous example where we were looking at the integral over c, z squared sine of 1 over z, which had a singularity at z equals 0. If we simply multiply now our function by z minus a, which in this case is z minus 0, so if we multiply by z, you see we'll just add or multiply to the z squared to make it z cubed sine of 1 over z. It does nothing to get rid of our singularity. So this example here is one where you have to do the Laurent series. Looking at our next example, we want to integrate over c e raised to the 1 over z squared. You see we have a singularity at z equals 0 because of this division by z squared. But you also see now if we multiply by z minus a, and actually because we have a singularity of order 2, we would be multiplying by z minus a squared. So z minus 0 squared is z squared. You see we will just have then a z squared e to the 1 over z squared. Again, it does nothing to get rid of the singularity, in which case we need to go and do the Laurent series expansion. Proceeding with this example then, doing the Laurent series expansion, C is the positively oriented unit circle. And the two things I want to note, again, e raised to the 1 over z squared is analytic everywhere except at the singularity, z equals 0. And since e to the z is analytic everywhere, its Laurent series expansion is a Taylor series. And this is another series we had worked out earlier, so I'll leave this work here for your reference, but the Taylor series ends up being z to the n over n factorial. And I just noted that here. The Taylor series e to the z is equal to z to the n over n factorial. Now I'm going to replace this z with 1 over z squared, so that's my function. So 1 over z squared in here, I'm still going to have my n factorial, 1 over n factorial, then z to the n, now it's going to be 1 over z, and actually it's not just to the n, it's to the 2n. I'm going to expand this out because I want to find the residue, which is the coefficient associated with the 1 over z to the minus 1 term. So let's look at this. When I plug in 0, I have 1 here, I have 1 here, so I have 1. When I plug in 1, I'm going to get 1 times z squared. But now, and I can continue, but you can notice then there's no term with just 1 over z, which means my residue is equal to 0, and that means my integral now is equal to 2 pi I times 0, so it's equal to 0. My last example is to integrate over c, 1 over z, z minus 2 to the 4th, where c is the positively oriented unit circle centered at 2. So here I have my unit circle centered at x equals 2. I can see I have two singularities, so 1 over z times z minus 2 to the 4th is analytic everywhere except at z equals 0 and z equals 2. But I also see this z equals 0 is outside of my curve C, so I'm not going to worry about it. It's not going to contribute anything to my integral. I only need to worry about z equals 2 and finding the residue at z equals 2. I'm going to look at my simplifying formula for the residue, and because z equals 2 is a pole of order 4, I have the formula for pole of order n. And again, this is for my singularity at z equals 2, and n is equal to 4. I'm going to look at what's inside these brackets, and I want wz times z minus a to the nth power. So I have wz, 1 over z, z minus 2 to the 4th, and then z minus 2 to the 4th will leave me with 1 over z. And this is exactly what we want to do. We want to get rid of our singularity at z equals 2. That's the purpose of this part of our formula. Now the second part is to take the derivative Which derivative do we take? It's d of n minus 1. So it's the third derivative of what's inside my brackets. So the third derivative of 1 over z. So when I take my first derivative, I get negative 1 z to the minus 2. I take my next derivative, I'll get minus 2 times minus 1, so that gives me the 2, z to the minus 3. And then I take my third derivative, and I get minus 6 z to the minus 4, or 1 over z to the fourth. And by my residue formula, then my residue is 1 over n minus 1, so that's 1 over 3 factorial. Limit as z approaches 2 of my derivative of wz times z minus a to the n, so that's minus 6 times 1 over z to the fourth, which gives me, and the limit, so the 3 factorial cancels with the 6, I'm left with the negative, and then here I have 1 over z to the fourth, and I take the limit as z approaches 2, which gives me 1 over 16. So my residue is now minus 1 over 16. I am going to work this problem one more time without using the simplified formula, just to show you how you can still do the Laurent series expansion. But I'm actually honestly okay if you want to skip this. This is my last example. You can end the video here. But in case you want to see the Laurent series expansion, in this case, I'm going to do the Laurent series expansion using the basic Taylor series. 1 over z is equal to the summation z to the n. Here I've rewritten my function 1 over z, z minus 2 to the fourth. I'm going to separate out my 1 over z and from my 1 over z minus 2 to the fourth, but I still need to multiply them together. This part here is exactly in my Laurent series form, so I'm just going to leave it. I'm going to work with my 1 over z. If I want it centered at 2 over here, I can subtract z minus 2, but I'll have to add 2 over here. This form is a lot like what we had done in our previous video when we were writing Laurent series. So here we have a simple function of z, z minus 2, that we could substitute for the z in the Taylor series, but we need this 2 to become a 1. So I'm going to divide the top, the numerator, and the denominator by 2. So I'm going to have, well, here I moved my 1 over z minus 2 to the fourth here, but I'm going to have 1/2, which I'm just going to factor out. And then 2 divided by 2 gives me 1, minus z minus 2 divided by 2. Because I'm going to want to plug this in to our basic Taylor series, I need to verify that my absolute value of z is less than 1, that is this here. So I need to verify that minus z plus 2 over 2 is less than 1, so I can use it in my Taylor series. Otherwise, my Taylor series won't converge, and this series formula won't be valid. So minus z plus 2 over 2, I want to verify it's less than 1. I can change this to a negative inside, introduce a negative. Since it's in the absolute value, I get absolute value of z minus 2 over 2 is less than 1. But since we know we're inside the circle, absolute value of z minus 2 is equal to 1, that means we know that z minus 2 over 2 absolute value will be less than 1. Which means we can plug this formula here, use this in our basic Taylor series. In my next line, I plug this in here into my Taylor series. So I have n equals 0 to infinity, my 1/2, and then this part here becomes z to the n. So my minus z plus 2 over 2 to the n. So this is going to be 1 over 2, this 1/2 with this 2 will give me 1 over 2 n plus 1. I'm going to factor out my negative 1 to the n, and then because I factored this out, this becomes z minus 2 to the n, and I already pulled out my 2. And last, I'm going to combine the z minus 2 to the fourth in here, so I get a z minus 2 n minus 4. If I'm looking for my coefficient of z minus 2 raised to the 1, so that's n equals 3, so my coefficient is going to be minus 1 to the third, and then 1 over 2 to the 3 plus 1, so that's 4, so that will be minus 1 over 16. So my integral is now going to be equal to 2 pi I times minus 1 over 16, which is minus 1/8 pi I. Last, I should mention we don't have to worry about the pole z equals 0 because it is outside of our contour. To review what we have discussed in this video, we talked about the residue theorem, which is a powerful tool for calculating both complex contour integrals and real definite integrals, and we'll go over this in a future video. So we first talked about the residue of a single pole. If we have a function and we want to consider the integral of that function over an arbitrary closed contour, so I is equal to the integral over c of wz. If we assume that wz has one singularity inside c, and wz can be expanded in a Laurent series about a point z0, such that the contour c is entirely within the convergence region, then the series can be substituted for in the integral. So in this integral for wz, we substitute the Laurent series expansion. And then we will find that the c to the minus 1 coefficient, in other words, the coefficient of the term n equals minus 1, is referred to as the residue at the singularity, and in general the integral is equal to 2 pi I, the c to the minus 1 coefficient, which is called the residue. And then we can generalize this. If we have multiple poles, our formula is then 2 pi I times the sum of the residues of poles inside C. There were some functions, like our last example, where instead of calculating the Laurent series out to find our residue to be able to put into our residue theorem formula, we have the simplifying formula for the residue. For simple roots, it's simply equal to limit as z approaches a, wz, z minus a. And you can see by multiplying wz by z minus a, we get rid of our pole. And then for poles of order n, we have 1 over n minus 1 factorial, limit as z approaches a, the n minus 1 derivative of wz, z minus a to the n. Again, this part here serves the purpose of getting rid of our singularity. So these two formulas can simplify things greatly, but we cannot always use them. There are only certain functions that these are good for, but they're great when they actually apply. So that's it for this video. Thank you for watching.